Let's talk about some examples of functions. In lots of your other classes, you've looked at doing r cross r, the real numbers cross the real numbers, and you've gotten a Cartesian coordinate system. And you were able to graph things like y is equal to 2x plus 1, which is a linear relation. This is something that's going to cross the y-axis at 1 and have a slope of 2, so it's going to be a line that looks like this. And when we talk about this in terms of a function, we can say f of x is equal to 2x plus 1. This is a function because every x value maps to one and only one y value. Every element of the domain corresponds with exactly one element of the codomain. Here we have another example where we have y is equal to x squared minus 1, which you may know is going to be a parabola, which will be crossing the axis down here. And if we write this in function notation, we say f of x is equal to x squared minus 1. This is also a function because every element of the domain, everything on the x-axis, maps to only one thing on the codomain. Something that may be useful for you when you're working with these kinds of problems, where you are looking at r cross r, a way of checking the second property to check that the x value only maps to one y value is to check it by drawing a vertical line through every x value. This is what is sometimes called the vertical line test. So the vertical line test tests that second part of our definition of being a function, and this also passes the vertical line test. Maybe in a geometry class, you looked at something like x squared plus y squared is equal to 4, and you saw that gave you a circle. Well, this is not a function. It's not a function because each x value maps to 2, or most of them map to 2. This one doesn't map to anything. This one only maps to 1. This one only maps to 1. And values out here don't map to any y values. But it's not a function, and we can see it doesn't pass the vertical line test. When you were in other classes, you may have done things like log functions, and they were functions because they were meeting these two conditions. When you did a trig class, you saw things like the sine curve would be functions. There's a discussion in your text about functions can be described as a black box where you put it in input and output comes out. Or you might think of it as a function machine. It's a very good image for thinking of how a function will work out. For every value you put in, only one value comes out. And that's indeed the way things work when you define a function in computer science. We can also examine things like having a function of a function so that we have the result of one function going into another function, going into another function. We're going to be examining how we can tell when functions are the same. Two functions are going to be the same if their outputs are going to be the same over the same domain. And we're going to see how we can do this with what's called functional composition. I'd like to look at one other kind of function that's more fun than anything else, but it kind of illustrates that this can be done with things other than numbers or letters. And these are not in your text, but I've seen them in other books, and I think they're kind of fun examples. Suppose we make up a set P, which is a set of all people, and I look at P cross P, which means we're going to be taking a look at all the people who've ever lived, and you're going to do pairings of one person with another person. We're going to make M be a relation. And that is a relation on P cross P, so it's a relation going from P to P. And we're going to say that the ordered pair XY is an element of this relation M if and only if Y is the mother of X. In other words, if we put X into the function M, it's going to produce Y, which is X's mother. So if we look at all the people here, we can say, Tom's mother is Sally, and Sally's mother is going to be Lisa, and I don't know, who would I make it? Bob's mother is Sally, and Lisa's mother is Sally. So we can have an arrow diagram like this. What we might say is this is the mother function, because everybody maps to their mother. And if we go backwards, looking at the inverse image, you're going back and looking at your child. So now my question is this relation, and it is a relation because it's defining a relationship between any two people in the set of all people, is this relation M a function? Does it meet the two criteria? Well, the first criteria is that for every element of the set of all people, when we take M of X, we're going to get something in the set of all people. In other words, we want to see that everything in this set here maps to here. Or in everyday language, what we're asking is, does everyone have a mother? So that first part of the definition is asking, does everyone have a mother? The second part of the definition says each element here should map to only one element here. In other words, it's asking, does everyone have only one mother? Well, since everyone has a mother, and everyone has only one mother, M is a function. You should try the rest of the problems that are in section 1.3, and I think this is going to be enough information for you to be able to complete that last group of problems in homework assignment number 4.